Hello, my name is Kyle Rojek, and this is part one of exam two. So in this exam, we'll be looking at the correlation of the evaporating mass transfer of a fluid on the inner walls of a vertical cylindrical tube. In part one of this exam, we'll be using dimensional analysis to show that Reynolds, Sherwood, and Schmidt's numbers are the appropriate dimensionless appropriate dimensionless variables that will be used in this problem. And to start out with the dimensional analysis, we'll be using the Buckingham Pi method to solve for these. And to start out with the Buckingham Pi method, we want to write out each of our variables in this problem. First one being the diameter, which is in meters. Then the velocity of the fluid, which is in meters per second. The density of the fluid, which is kilograms per meters cubed. The viscosity of the fluid, which is kilograms per meter seconds. The mass diffusivity, which is meters squared per second. And then the mass transfer coefficient, which is also in meters per second. And next, in the Buckingham Pi method, you want to make a dimension matrix. And to do that, we'll write the variables across the top. And then the parameters, kilograms, meters, and seconds across the side. And in this matrix, we want to write out the number of each parameter that is contained in each variable. So the diameter contains 1 meter, velocity, a meter and a second, density, 1 kilogram and 3 meters. The viscosity has 1 of each. The mass diffusivity has 2 meters, 1 second. And Kc has 1 meter and 1 second. So next we want to determine the rank of this matrix. That is done using linear algebra. And it is determined that the rank of this matrix is equal to 3. And again, using the Buckingham Pi method, we know that the number of dimensionless groups that we will have is equal to the difference in the number of variables and the rank. So with 6 variables and a rank of 3, we will have 3 dimensionless groups. We'll name those pi 1, 2, and 3. So what each of these dimensionless groups will contain is equal to the variables in this problem. And to determine what variables go where, each of the 3 dimensionless groups need to have 3 variables that contain at least 1 kilogram, 1 meter, and 1 second. So in those, we will have mass diffusivity, the diameter, and the density. It's the same for all 3. And each of these are going to be risen to their own respective exponent, a through I. And then the remaining 3 variables will be placed in each of the 3 dimensionless groups. So Kc, velocity, and the viscosity. So next, in the Buckingham-Pi method, we want to determine the values of these exponents. And to do that, we want to expand each of these variables with DAB being meters squared per second, diameter having meters, and the density being kilograms meters cubed. And also with the mass transfer coefficient having meters per second with an exponent of 1. And then it's the same for pi 2, because velocity and mass transfer coefficient contain the same parameters, meters per second. And then pi 3 is almost the same, meters squared or per second, meters, kilogram meters cubed, and the units for viscosity, which is kilograms meters second. And so next we want to determine the values of each of these variables. And to do that, we want to start out with the meters in pi 1. That is equal to 2a plus b. And we can see here that c is equal to 0 because there's no kilograms in Kc. So plus 1 to 0. And c is equal to 0 as well. Next is seconds, which is negative a minus 1 equal to 0. So we can see here that a is equal to negative 1. Then using this information, we get b is equal to 1. And so that's the same for pi 2 with d equal to negative 1, f equal to 1, and e being equal to, e equal to 1, and f being equal to 0. So next is pi 3, which is a little bit different from pi's 1 and 2. So we'll start out with meters again, which is 2g plus h minus 3i minus 1 equal to 0. And seconds, which is negative g minus 1 equal to 0. So from this, we can see that g is equal to negative 1. Then kilograms gives us I plus 1 equal to 0, making I equal to negative 1 as well. And solving for h, we get h being equal to 0. So plugging in their respective variables, we get Kc times diameter over mass diffusivity pi 2 and then pi 3, which is the viscosity over DAB and the density. So we know that this is equal to Sherwood's number, this is equal to Euclid's number, and this is equal to Schmidt's number. And so to obtain Reynolds number, we're going to divide pi 2 and 3. That gets rid of the mass diffusivity, leaving velocity, diameter, and density over the mu, which is the viscosity of the liquid. And that is then equal to Reynolds number. And this is how you use the Buckingham pi method to use dimensional analysis and show that Sherwood, Schmidt, and Reynolds numbers are the appropriate dimensionless variables.